So hi guys. So today we are going to see the C question that appeared in the weekly contest of Leetcode, and this is a good question. The question. Let's go to the question. Uh, yeah, here it is. So this is the basically the question. Let us look at it carefully and. Uh, by solving this particular question, we would be covering various topics, and also we would be covering two questions which are kind of a prerequisite of this question. But we would be first looking at this question and then those two lead code questions, which are essentially lead code hearts, but kind of make more sense and would be pretty much easy. Right. So the question is pretty clear that the name of the question is concatenated divisibility. Okay, so I have been given an array of positive integers nums and a positive one for ones. I wanna check. Yeah, it is getting recorded. Actually, last time it didn't get recorded. Okay, so I have been given an array of positive integers. Okay, and an positive integer k. Interesting. A permutation is said to be form a divisible concatenation if when you concatenate the decimal representation of the numbers in the order specified by the permutation, the resulting number is divisible by k. Okay, so and what we have to return, we have to return the lexicographically smallest permutation when considered as a list of integers that form the divisible concatenation. Okay, so if no number exists, we have to return an empty list, right? Okay, so first of all, this is not very obvious. You might go wrong in the first go only after reading this. Let me tell by an example. Let's come on the iPad. So basically, this is the question. Topics to be known is definitely dynamic programming, bitmasking, and reconstruction of DP. And other similar questions are two lead code hearts, which we would be discussing. Right? Let me see. Yeah, it's totally coming. Right. So uh, what does it mean by lexicographically smallest based on the integers? So this basically means that if I am being given 5 and 1 5, right? So you might think that after concatenating it, it is best to concatenate like this is the first number and this is the second number. You would think that after concatenating it, this is the lexicographically smallest number. But no, this is not. The answer is 515 only because they are saying to be concatenated uh by the number. They think that the smaller should come first. So this is what they mean by lexicographically smallest string. Interesting. So let's come back to the question once again. I think we now understand what the question says. Now let us look at the nums. Okay, so let us think of this particular test case. So let me write it on my iPad. The nums given to me is 3, 12, and 45. 3, 12, and 45. And the value of k is equal to 5. Interesting. So what it is saying is that out of all the permutations that are possible, right? So first of all, let us think that how many permutations are possible. So number of permutations possible is 3 factorial, which is equal to 6. So it is saying that out of all the permutations possible, I have to return the lexicographically smallest permutation, which is divisible by this k, right? So this looks like if n is around 7, then we could have simply done an n factorial approach and this would have worked perfectly fine. But let us see what kind of constraint is there in the problem. So the constraint in the problem is okay. So the constraint in the problem is that what n is equal to 13. So n factorial is out of picture. Okay, interesting. Now whenever n factorial, usually, I'm not saying that this is any sort of hard and fast rule, I'm saying usually when n factorial goes out of picture and n is still like around 13. So they are kind of hinting us to go in the direction of an exponential solution because, of course, 2 to the power of 13 is around what? 8 into 1024. So around 8 E3, and we can basically, it is something to think about that. Yeah, we can think in the direction of exponential solutions. Okay. So let us solve this question now. So basically, let's put the iPad, right? So what are all the possible permutations, right? So it is either I can write 3, 12, and 45, or I can write 3, 45, and 12. Right? Either I can write 12, 3, and 45, or I can write 12, 45, and 3. Either I can write 45, 3, and 12, or I can write 45, 12, and 3. Interesting. So after concatenating it, the number that I would get is 3, 1, 2, 4, 5. Yes, it is indeed divisible. 3, 4, 5, 1, 2, not divisible. 1, 2, 3, 4, 5. Yes, divisible. 1, 2, 4, 5, 3, not divisible. 4, 5, 3, 1, 2, not divisible. And 4, 5, 1, 2, 3 is also not divisible. So the only possible divisible things are this and this. And out of that, I have to tell the lexicographical smallest. So it is not this, because here 12 is coming and here 3 is coming. So this is the lexicographical smallest number. So like sequence, so the answer to this would be 3, 12, and 45. Let us see what's the answer. Yeah, here it is. 3, 12, and 45 is the answer. Similarly, in this particular case, this is a smaller test case, so I think I can be done over here only. So I have numbers 10 and 5, k is equal to 10. So I think the only possible is 5 and 10. Yeah, 5 and 0. Yeah, yeah, exactly. This is the only possible. So this is what we have output. And for fourth, there cannot be any permutation which can be made using the numbers 1, 2, and 3, which is divisible by 5. Thus, we have to return empty vector. Interesting, interesting. So let us now think what what else. Basically, we have totally understood the question, what it is trying to say, right? So let us come again to the iPad and start thinking. I won't tell you to directly jump onto about thinking in the direction of DP bit masking. I'm just going as the question is directing me to, right? The direction in which the question is directing me to, right? So one possible solution that is coming to my mind is I can maintain some sort of a particular uh, like something like 2 to the power of n solution might work easily. In fact, this would go around 1024 into right around 1e3 1024. Oh, I'm bad. 8 into 1024, so around 8e3, right? So this might be something related to the time complexity, right? Also, because I can make all the subsets, right? Basically, in we know that if I need to represent some kind of a subset, I might represent it in form of a bit mask, right? So this is the way in which I might think around the direction of bit masking. However, let us first take this example only, which is 3, 12, and 45, right? So this means that after what is my aim, let us write the aim, that after taking all the integers, taking 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 all the numbers and modding that number with k, I should have a zero. Very interesting. So it is okay, right? This is kind of the thing that we are thinking. This is my aim, right? So if we think totally brutally, thinking about recursion is an obvious way to go. Because what I can do is that either I can use 3, 12, and 45 for the numbers, right? Either I can put 3, right? And then go about putting the other two numbers. or I can put 12 and go about putting the other two numbers, or I can put 45 and go about the numbers. The k was equal to 5, right? But I need to make sure that after I mod this whole with what do we say, this basically it means basically finally when I get the answer, modding that particular answer with k should give me a 0. Very interesting, very interesting. So what we can do is that we can kind of say that what do we want, that I can basically put any of the numbers, this or this at the first position, right? So what can I do is that either I can place this, either I can place this, or I can place this. Okay. So if my DP is like, if this 3 is represented by 1, if this 12 is represented by 1, and this 45 is represented by 1, this basically means that in my subset, I have taken this number, and this number. And this might have would have come either from I had taken this number first and I had taken this number. I had taken the middle one and I had taken the last one. And I had taken the first one and I had taken not basically took the first one and not take and had and already had the last one. What does this depict? This basically depicts that each subset is to be taken as a bit mask. And what is a bit mask? It is a way of representing a subset, right? I think I want to make sure that I'm recording or not. Okay, I hope I'm recording. Yeah, I am recording. Interesting. Okay, right. So this automatically gives us a hint that yeah, DP basically considering that I have any sort of bit mask which is say represented by any number 10110. This is the current number. This basically means that if I number my uh, like vector values like first number, second number, third number, fourth number, fifth number. So this bit mask represents that if ith bit is set, this means I in my set, in my subset, in my subset, I am considering the vector given to us. Interesting. So this is my way of representing a particular subset, and this might have come from any of either this was the first, this was like the last one that I added, or this, or this, or this. Also, I can say that if this is 0, what is the next particular thing that I can add? It is either this element or this element, isn't it? Because in currently in my subset, this is 0 and this is 0. So what I can do is either I can add this to the front or I can add second element to the front, isn't it? So this basically means that if currently I am having DP of any sort of mask, or I say any sort of subset, and from that subset go to subset where a new element. How can I add this particular element? I can add for all those bits I which are unset in my this subset, or basically not present in this particular subset, right? So this is the intuition that I'm having, a little bit of intuition. Now let us further dig upon the question, right? So at any particular situation, if, and what do we want? That after taking all the elements, I should have a remainder of zero, isn't it? So basically, what is my aim? My aim is that after taking all, aim is after taking whole set, I should have remainder must be equal to zero. This is my final aim. This is my final aim. Interesting. This leads us to this particular DP where one parameter is whole set and one parameter is the remainder. Because the value of k. Let me see what are the possible values of k. Let me see the values of k. Sorry for a little delay. Sorry for a little delay. The value of k is still only 100. Interesting. So, iPad. Yeah. So, k is greater than, of course, I guess. One, it must be one. Let me see once more. Okay, yeah. K is greater than equal to 1 or 100, right? Okay. So, this is again giving me hint further. Interesting. That this might be the correct DP state which I'm looking. And this whole set, and this particular whole set is basically 2 to the power of n. And a particular subset can be represented as a mask, isn't it? So my time complexity becomes 2 to the power of n into k, which is like, because n was 13, so I somewhat took that 1e3 is equal to 2 to the power n and k is equal to at max 100. So my DP state should at max be 2 to the, like around 8e3 into 100 or 8e5. Okay, totally fine. This is about what could be the transition that I'm making. That is because I am having currently mask the subset and I want a remainder. This basically means that from this particular subset, basically this state defines whether using the first I this state defines that whether using the mask subset. And what I meant by mask, I already told you that the bits that are set in my mask are the, actually, if the ith bit is set, this means that in my subset I am considering the ith element, isn't it? So this state defines whether using the mask subset I can make the ith, oh sorry, if I could make the remainder is equal to, this is basically a boolean DP state which defines that whether using the subset defined by the mask I could make remainder or not. This finally provokes us to think about, okay, we have thought about the DP state. Now let us think about what kind of transitions can I have. Okay. So if I'm having a DP of mask, isn't it? And I have a particular remainder. So if my mask is of 10101, right? What I can do, I can either make 11101 going on this element, either I can make 10111, right? These are the only two options. So let us explore that, isn't it? So from a particular DP of mask, if any element of this particular mask is zero, if any particular element, like I thought, I think that you got, oh oopsie, I hope that you got this particular part. So if any bit of my mask is 0, means I can add that bit to my mask, isn't it? Then what would be my mask? Say ith ith bit is unset. Okay. This means that dp of mask, comma remainder. If this is true, this means that if I kind of like add the ith bit, then my mask would become mask and oops, sorry, a little water spill over. Mask XOR with ith bit, right? That would be the new mask that I would go to. But one thing over here is extremely interesting. Because using the mask elements, I got remainder equal to rem, right? And as I told you over here, that I had a chance either, basically, I had a chance either I could put the second element in front or I could put the fifth element in front. So thing is that the new number that I would have created using the mask and the number the number at ith bit, right? So my remainder for the new mask would have changed, isn't it? Isn't it very obvious that if using three elements, I was having a remainder of say 2, and I added say 4 at the start, right? So my new remainder would, it was 3, right? And I added 4. So my number became 43, right? And what is the actual contribution of 4? It is actually 40, isn't it? So basically, so basically, my new remainder, what would be my new remainder? It would be basically the additional, new remainder would be actually the additional, basically, what, how do I say that? Uh, because I already had 3 as the remainder, right? Now, because addition of 40, what would be my new remainder? This would exactly be 40 plus 3. Also, this would be mod k, right? Because if using the current elements of my mask, I am getting a remainder of rem, right? And after adding nums of I in the front, this means that there would be some permutation of my mask elements, and I added I added the ith element in front. I added the ith element in front. This basically means that I added this particular number into 10 to the power of 1, 2, 3, 4, 5, 6. 10 to the power of 6 as a value to my new number, isn't it? So, my new remainder that would be set in my new mask would be actually accumulation of this particular remainder and the remainder that have been caused due to this number, isn't it? And how can I calculate this new remainder is actually a question. Till now, we have seen that, let me write it down. We have seen permutation of mask elements. By mask elements, I mean all the ith set bit elements, right? Basically, if the bit is set, then I have taken that as a subset, right? Okay. Uh, we have seen using some permutation of the mask, or by mask you can also mean the subset. We have seen using some permutation of mask, we obtained remainder is equal to rem, right? Now by adding a value equal to some permutation is over this and adding this particular value, the new remainder would have accumulation of this particular number also, right? And how can I get that particular additional accumulation that have occurred and have caused a new remainder to occur? That is an interesting thing to look at. The interesting thing over here is that this was 53. No, say this was 101, say this was 10, say this was 101, say this was 101, 1, and 101. Right. So, what I need is say, and say just one examples. Let's not think in binary. Say this was 53, say this was 4, this was 3, this was 2, this was 8. So, what is the cumulation? That cumulation of the remainder, basically additional remainder that this particular number have added, right? This is basically its value, actual value. This is basically say this was 54. So the permutation that have been caused, say this was x, right? And what have I actually added? I have added 10 to the power of 6, isn't it? And what is this? This is actually the length 2 plus 1 plus 1, 4 plus 1, 5 plus 1, 6. This is the actual added. So the additional number that is added to make a new remainder is actually 54 into 10 to the power of 6 mod k, isn't it? And if j was the original remainder that I had for the current mask, for the new mask, the new remainder would become this. A very important thing in this question, how to get the new remainder. If this is the current remainder for my mask, and this is the additional value that I have put in front, then what is the new remainder? This is the new remainder, isn't it? Instead of 54, I can write nums of I. This again tells us that initially I had 2 to the power of n into k dp, but each for each subset for each subset I must have I have to mask of length n to explore what all places can I go. This means the time complexity would be 2 to the power of n for each mask. For each remainder that it could have, I would have into k. Each particular mask, I need to check that whole mask, and that would take me in. So the time complexity would somewhere boil down to, I think I had 5, 8, 5, I'm not wrong. And okay, let me write it. Okay. 8e5 multiplied by 13. And 14, 8, 60, 8, 80, 104. 104 into 1e5. So I hope it's correct. 1e7, around 1e7. So this is well under the constraint of 1 or 2 seconds. I don't know what Leetcode has the constraint as time limit, but 1 or 2 seconds, whatever it is, this would definitely work. So I have got a little intuition that if I have that initially I had that 0, 0, say I had 5 elements, so 0, 0, 0, 0, 0. I think this would be very big, 0, 0, 0, 0. And for that particular 0, 0, if I had no elements, right, then what is the remainder that is possible? It is 0, right? Because I've not even taken any element. Remainder of only 0 is possible, right? So from this, what can I do? Either I can put the first, second, and third. What can I do? I can either place the first element 100 new remainder that I've already taught you how that new remainder came, or I can do 0 1 0, then again new remainder. These are different, like new remainder 1, new remainder 2. And or I can do 0, 1, 1, remainder 3. This is the kind of transitions that I'm thinking. So let us now formulate a little more formally. What would be my answer? Answer would be that after I take whole set, this means that in my mask, all the bits should be 1 because 1 means that I've taken that particular element in my set. So my answer would be that dp of whole set. And what is the remainder that I'm trying to achieve? Rem should be equal to 0, isn't it? So that is actually represented by a bit mask. And what bit mask that would be? Ask yourself. It would be 2 to the power of n minus 1 because here all the n bits would be set, isn't it? So this is what I'm thinking. This is the basic crux of the problem. But one more thing is very important. Let us try run this particular case that I had. Let me go to that particular test case. 12 and 45. Interesting. Let's try run this. 3, 12, and 45. Initially, what I had as true. First of all, I'm right now my DP state is basically they're not only asking us to say yes or no whether it is possible or not. They are telling us to even print that particular subset. So the question is actually very good. This is we are not even halfway to the question. So this there is a lot to learn from this particular question, isn't it? Right. So initially I had that 0 comma 0 comma 0 for this particular subset. I have 0 as the remainder. That is for sure. That is definitely achievable. If I say that if I add 3 in front, right, my bit mask would look like 1, 0, 0, right? And because I want k and I add the value of basically the value of k was 5, right? So this basically means that after adding okay, so basically after having 3, right, after I had 3 and initially I had nothing. So 3 plus 0 mod 5 which is equal to 3. So I just had that using this particular subset, I can have the remainder as 3. This is what I have gone, right? Then over here, I can say that after I set this, then I had 12, right? So 12 mod 5 plus 0 because I had nothing, mod 5. So mod 5, it would be just this only. So it's 2, right? So that's there, isn't it? And if I add this, then it would be 0 comma 0 comma 1. And if I add 45, then it would be 0, isn't it? Now, it is very interesting that now what there could be a lot of ways, right? Answer because answer could be 3, 12, and 45, and 12, 3, and 45, right? And I have to get the lexicographical smallest one, right? So basically, this kind of means that okay, we will go on to that particular part later on. So we have basically gone through the first basically part of this question that whether to tell is it possible or not and the kind of what do we say dp that we had, that is around 2 to the power of n into k, which is well under the constraints, right? So let us look at that particular part of the okay, over here let me have a quick go through of what that particular part of code would look like, right? So I would have that dp of 0 comma 0 is equal to true because using the zeroth, basically not choosing any elements, not choosing any elements, I am sure to have remainder is equal to 0 because the number that was termed is 0 obviously. So the remainder is also 0, so I can say yes. Therefore, I or I can say mask is equal to 0. Mask is less than 1 L to the power of mask plus, right? Okay, mask plus plus. This is basically I'm iterating through all the masks for each particular mask. What are the possible remainders that it can have? For remainder is equal to 0, remainder is less than k, of course, remainder plus plus. Now, for each mask, explore the unset bits. Saying explore the elements that have not been taken in the mask right now. So I go on continue already in my set. Do something about it. What I have to do something about is extremely important because that is how I would make a transition. So this particular mask and this particular remainder, if it is achievable, this is extremely important that this must be achievable. I can't do from something that is not achievable. So I definitely need to make sure that if mask and remainder is false, that unreachable, continue from here. This is totally unreachable. Sorry for the handwriting. This is reachable. So if it is reachable, then why don't we go to more and explore more? Right? So what would it affect? It would affect mass, ith bit, isn't it? And what would be the new remainder? This would be true. And what is that particular new remainder? That is what I have told you just before that that this particular new remainder is nothing. New remainder is nothing but the number added at front plus in basically number added at front. Oops. Oh, where is it? Yeah. In fact, not only number, contribution. Contribution of number added at front plus what is the initial not j, in fact, remainder that I had mod with k, right? So this is what it is. This is this. Yeah, this is what it is. This is the basic code which would tell me that TP of any subset and any remainder, whether this is possible or not. Possible, not. Also, it is very obvious to see that if my DP of my set, which is represented by 1, 1, 1, 1, 1, or simply 2 to the power of n minus 1, and 0 is false, this means that, bro, we don't have any sort of permutation possible of of all the sets which could produce a remainder as 0. Thus, I would simply return an empty vector. So let us look at the code once for this particular. See that the question is not over. I don't know how many people solved it. I was not able to solve it in my first go. I took a little help, but then it was pretty much obvious and clear. Right? So we will come to this. We will come to this. But why we wrote this? This is a very obvious go-to thing, right? So, of course, when k is equal to 1, of course, k is like every number. like this would basically any permutation would be possible. So we would basically return the sorted form, right? We will come that why did we sort. We will come to this part also, right? But currently we don't know, we don't need this. We are basically looking this 32 to 44th line. You must, or basically 45th line, you must know this, right? So I basically went on to mask. I don't think this would also create a problem. I went on to each mask, and if that particular mask is not possible to achieve, then I would simply continue. Then I went on to each particular bit, going on to each particular bit. And if that particular bit is already set, then I don't have anything to do. Otherwise, my new remainder is basically remainder plus nums of I modulo k into power of 10 of length of mask modulo k. This is a very bad thing, but I will break it down for you so that it becomes very much obvious and very much clear. Right. So let me write it once. Equal to remainder plus nums of I mod k into power 10 oopsie power 10 of length of mask. Okay, so very bad thing. But no worries, this is very obvious. You would soon realize that, of course, Shivam, what else could you have done, right? So where is my iPad? Here is my iPad. Right. So this is basically my new remainder. Right. I hope that this particular part, like this whole thing is clear, right? And this might be a little intimidating or a little tough, right? So what is this? This is one thing is for sure that this is a contribution due to the ith bit added. This is pretty much obvious. Right. So just take for an example. As I already said, like let I had 53, 43, 24, 50, 35, 36. And if I added 56, what would contribution be? It would basically be 56 into what are the total number of digits here? Which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 to the power of 10. This would be the contribution, right? So just leave this, right? So now isn't it making very much sense that nums of I, which is the number, and the power of it, 10 to the power of it. I could have written 10 to the power, but it was not working because this is going out of the long integer range, right? So I need to mod it everywhere. So this is basically 10 to the power length of the mask. And if and can this be pre-computed? Definitely. Because what is this? That if I say what is length, if I say that what is length of 10101, 1010, and I add the numbers 45, 2, 3, 5. What is the length of this? This is basically if this number is set, this number is set. What is the total length? 2 plus 1, which is exactly equal to 3, isn't it? So, for any particular mask, I can already pre-calculate the length that I can have. The length came out to be 3, isn't it? So, yeah, this is what I have done over here. That for this particular new remainder, I calculated the powers 10 to the power. And let me also have a constraint on this. What's the maximum power of 10 that I can have? This is basically the maximum number of digits that I can have, isn't it? And before putting any sort of number, at max I can have all the like n minus 1 numbers, and each number is between 1 to the power 10 to the power of 5. This means it can have like 10 to the power of 5, right? So it can at max have 5 digits, right? So when I have 13 numbers, right? So at max there could be 10 to the power of like somewhat 60. This is the maximum. But I calculated 10 to the power of till 199. I calculated it till here. So this is pretty much very much like what do we say, very much obvious thing. This would definitely work, right? Even if I show you my solutions, I also added didn't initially didn't add this. What do we say? Yeah, this was the error that I was getting when I was not pre-calculating it, right? So this is what it was. Yeah, I simply had the remainder plus nums of I into 10 to the power of length of mask. I directly did this. So yeah, this was giving me an integer overflow. That's why I pre-calculated this particular thing. So I hope that now that particular portion of code is not looking tough for you, right? This like from line 25 to line 31. This is totally clear, right? Now, now basically, if it is pretty much obvious that if this particular DP state is false, then I have to return an empty vector. Now comes the question that actually was basically I was able to do till here, and the reconstruction part was actually kind of tough for me, and for that I took help from somewhere, and I'm really thankful to him. So I don't know whether I could take his name or not, but yeah, I am very thankful to him that he explained it very well, and I hope that I'm also explaining it very well to you. I hope that it helps a lot. I am basically exploring all possible things in this particular question. That this particular uh is the part. This particular is the part where it gets interesting, right? Okay. So one thing is for sure that now I know that I yes there is some particular permutation that after modding with 5 after concatenating it and modding it with 5, just listen to me very carefully, that there is some permutation that after concatenating and modding it with 5 I would get 0, but I don't know where what is that particular permutation. What I know is that that there exists a permutation, right? But one thing that I know is that one of the numbers that would be in the front, isn't it? This means, let me come back to my iPad. Okay, let us come back to the iPad. Yeah, this basically means that I know that yes, 1 1 1 1 that for this particular you remember this is very much possible. And this could have come if I had put this particular number in the front. Particular number, right? I'm not considering basically remainders right now, or this particular number, or this particular number, and basically 0 0 and goes on. Any one of oops, I think I did a blunder. 1 0 1 1 1 1 and 1 1 0 1 1 1 something like that, right? Any one of this bit would have definitely come. So if somehow I could maintain that where did this come from, then I would definitely reach my answer. If I say that this was the correct path, then I say that yeah, this is the way. This is the way that you are going, and this is totally correct. And I also need to make sure that if there are multiple paths, say that from here also it is possible. I also need to make sure that the number that I am adding, like say this number I am adding or this number I am adding, I need to make sure that I add the smaller one because I need the lexicographically largest permutation, smallest permutation. Right. So this basically means that basically this particular number is definitely greater than this particular number, isn't it? Isn't it very much obvious that this particular number is definitely greater than this particular number? Oh, no, no, no. In fact, this particular number is greater than this particular number, right? And while I am going from 0th bit to the last bit where all bits are set, I would encounter this number later than this number. This means that if at this particular position I had a smaller number and this is a correct path, it would final update my this particular state. Let me take a better example because this is actually interesting. That why are we sorting it? Right. Let us take that example only. The example was it is 3, 12, and 45. 3, 12, and 45. Right. So what could have happened? Let me write the two scenarios where yes was coming. Right. So it was either coming 3 I took first, and then basically there was this particular set. Right. Set was 12 and 45, or I could have taken 12 and the set was 3 and 45. Then either I could have taken, then there is only one choice, that 3, 12 and 45, or 12, 3 and 45, right? So these are the two basically numbers that are possible, which would give me a result, me a yes, right? So what I'm saying is that for each of this, oh sorry, that for each of this, if I somehow had a link to this particular DP state, then I could simply say that yes, this was the this was basically this is my current mass, this is the previous mass, and if I XOR, then I would know that 12 XOR 45 XOR 45 XOR cancel. I had 12. This means that 12 was the number that was added, and I would simply add it to my answer. But I also need to make sure that my 12 that is added is actually the smaller of all the possible paths. And how can I make that sure? Because 12 is, let's see, that, okay, let's see, that I have a path to this. Basically, this is also a correct way, this is also a correct way, this is also correct way, and this is also correct way, right? So, okay, so in fact, just think that, right? The basically I can go from here to here also, and here to here also, but my answer is here to here because this is the lexicographically smaller number. This means that out of 12, that whenever I am putting learning, please let me check once my voice is getting recorded. Voice is getting recorded. So yeah, basically the matter of fact is that this is not this particular set. This is like I had the lowest one, then the highest one, and the most highest one. Then I remove when I remove three, basically it would become 0, 1, 1, right? And this would become, yeah, this would become 1, 0, 1 becomes 4 is, oh no, not even that, yeah, because 1, 0, 1 exactly, because 12 is getting right, 12 is getting removed, right? So if I go from with, yeah, it was such a good error, I would say, because it's very tough to debug it during that solving it live, right? So yeah. So this particular means that I have even linked to this, I have linked to this, I have linked to this, I have linked to this. From this particular point, and this particular point, I would have gone to this, I would have updated this, I would have made a link to this. I'm not saying how to make a link. Currently, I'm just saying that we have the power to make a link. If somehow we make a link, right? We always want a lower number to always come first place, right? Whenever I'm iterating through like this, of course, this set will come before this set will. And if this particular bit mask has the power to update this particular bit mask, this simply means that this is a better way to go to, because after adding 12 in my number, right? Because after adding 12 in my number, I accept that yeah, this is one of the path that is achievable. But always remember that it is better to have three. That it thus it is always better to have the number that is lower to come at the first position to make it lexicographically smaller. And how can I make it? After sorting this, because when I sort this, and if I see that I remove because I'm iterating from 0 to the power of n minus 1, and I would encounter this with first. This means that I will always try to remove a bigger number first. And because I'm trying to remove a bigger number like 12, and after that I get yes 12 after removing 12 there is a valid path. But then I get that for this particular bit mask this is also achievable. Remove 3. So this is the better way to have a link. So basically this is a better link to have. So for this link it would remove or update that link to this link. So this is the link that I am having, right? So this is the imagination of linking that would happen, right? So this is what right. So simple as that. That after that my bitmask would for this particular my bitmask because I remove 45 and 45 is the largest, so it would be like 0 1. No, I removed 12, right? So 1 0 0 and then finally 0 0 0, right? So this is how my linking would look like. That this mask would be connected to this. Basically, I would have this. This mask would be connected to this mask. This mask would be connected to this mask. This mask would be connected to this mask. Right? And the teacher from whom I also studied, he made a very beautiful. What do we say that? He made a very beautiful explain this that I had say 3, 45 and 12, right? And after sorting it, I had 3, 12 and 5, right? So, oops, so my pen is getting so. This is the numbers and possible configuration are 0 0 0 like make it not we make any terms 0 1 1 0 0 1 1 0 1 0 1 0 1 and 0 1, right? And so, and what are the values of k? The values of k are basically k 0 1 2 3 4 5. And initially, I only have this as true, this as false, 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 false. Let me do it fast. Basically, this for any f means that for any particular mass, currently this particular remainder is empty. Right. So let us have my tabulation table. Right. This was true. Very much true. Then I said that I can either set this bit or I can set this bit or I can set bit. Okay. Definitely I can do any of. If I set this particular bit, what is the value of k? What is the value of oh oops. This is not possible because remainder can only vary from 0 to k minus 1. So if I had because I had k is equal to 5 and initially I had 0 uh after adding 3, this means that I've added 3 to my number. Like the confusion that I got was because of this only. I thought that I added 45, but no, I added 3 over here, right? So after I added 3, my remainder would become as 3, right? After I added 3, my remainder would become 3, isn't it? So what I did that for this particular mask, this is true. That yeah, after adding, this would become true, right? For this particular thing, if I added 12, then I would say that this would become true. Sorry, it would become true. After adding 45, I said that 0. This would become true. Now I said that from this particular mask, where I can go, I can either go to over here, right? I can either add, what do we say, uh, the number 12, right? So initially I had 3, then I added 2, then it would become 0. This means that for this is possible. Particular mask, it is possible to achieve the remainder as 0. That is after taking 3 and 12, right? From here, I could have also gone to here, right? And for that, what would be my answer? That 1 0 1 And I had taken 45 and I have taken 3, right? So 45 plus like 45 mod 5 is 0, 3 mod 5 is 3, and 0 plus 3 mod 5 is also 3, right? So for this, 3 would get set, right? And for this particular and from here I could have gone to here, right? And after going from here, because 3 is set, and what I am remaining is 12. So 12 mod 5 is basically 2, 3 plus 2 is 5, and 5 mod 5 is 0, right? So this became true, and this is what we wanted, right? We wanted that after choosing whole set, my remainder should come out to as 0, right? Interesting. So, but it's not over yet. So, what was the optimal way? The optimal way was to choose three first, right? So, I kind of chose three, and then after choosing three, I went on to 12, if I'm not wrong. So, from here, we went on to here, and we chose 45, and 45, we chose 45. We is wrong. 12. Okay, so basically the contribution of putting three. Okay, so basically we had when I okay, so okay, right. So basically from here I chose the number. Okay, right. So this particular state I might have like this is very much achievable from 0. So initially I had remainder 0. If I chose 3, so my this would be set the first bit, right? So I would have gone here, right? So answer would be 0 plus 3 mod 5, which is basically 3. Interesting. Would have gone as through. After being here, I added 12, and the contribution of 12 would be 12 and 3. So 120, right? Mod 5 is 0, right? So uh, mod 5 is 0, right? So 3 plus 0 mod 5, right? So from here I would have gone to 0 1 1, right? So 0 1 1 over here, right? And for this I would have gotten a true, right? And after that I would have added 45, right? So what would it make? It would basically make uh basically make 120, would basically make 100, and basically 3 plus 45. Okay. 45. This is actually working correctly, not the correct path. This is like I could have gone to 100. This is the correct path. So I want to 100, right? And then my remainder would be 0 plus 45 minus 5, 5, so it would be 0, right? So this would become true, right? This would become true. And from here, I could either take 12 or I could either take 3. If I took 12, then it would go to 110 over here. So, and my new remainder would be 0 plus 12, and due to 45 there are two digits, so the contribution would be 1200 mod 5, mod 5 over here also. So 1200 mod 5 is 0, mod 5 is 0, right? So this would also set this particular thing, and when I would add, then it would, the contribution would be 12, 45, 3. So for the 4 digits, the contribution would be 3 into 3, 4. Mod 5 would be equal to 0. So here, this particular bit, this would also be set, and this is what I want. You can also try other paths, and but you will realize that this is the most most the best possible path which I could have, right? So I just added. So basically, you just saw that the number 3 was the last number that I added, right? And this would only come if I would have sorted the array first, right? Because that's the last least, because this 3 is represented by this particular bit. Like in this bit, 3 is not taken. Here it is taken, not taken, taken, not taken, taken, not taken, and taken, right? So this would be the last when I would be iterating through all these possible. When I would be iterating through all these possible, this particular 0 means that basically this particular 0 means that I took the highest possible number. Then it says that I took the one less possible number, right? Then it would be I took the one less possible number. And for last, this would say that I took the least possible number. And this would be the last one to come, right? So yeah, this is what it is. That is why it would impact it, the, the most, because if it is possible to come from here, then this would be the actual link that it would have, right? Interesting. Now is the link that I need, right? So basically from this mask render, we need a link to this place, a link to this place, and from here I need a link to this place, right? And from here I need a link to this place, right? So for each particular mask, like I already told you, that for each particular mask, I would have require a link to the previous state it came from, right? So I actually simply did it using the concept of reconstruction DP. I basically stored that from where that when I was making my recursive solution or the basic iterative solution, from where I basically set that particular bit. Basically, I simply said that if this was the mask and this was the remainder, and from this particular mask, I set a new mask and then basically I can say that parent of this particular new mask remainder is nothing but mask and remainder. This basically means that for this answer, basically this is the whole set, would be a parent which it would be connected to, which would have one unset bit, right? Say this was the optimal path it came from, 1 2 3 4 5 6 1 2 3, and say then this is the most like the most optimal path it came from, 1 0 1 1 2 3 5 1 2, right? Like this it could, and it would go on to 0 0 0 0 0. So it is always best that I go from here to here, then from here to here, then from here to here. And I know that when this was the transition, I added this particular bit, right? And how can I make sure this? Basically, simply XOR. Then this would cancel, this would cancel, this would cancel. this cancel, 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 cancel. Only this cancel, cancel. Only this bit would be left. Right now, if I calculate the trailing zeros, say 1, this means that the element which is at the first index is the one that is added at the front, at the total front of my final permutation. That is the answer. So like this, my answer would have been created, and that's why we need to sort the array. I hope that sorting the array also makes sense. Please don't get confused. The part where I got confused, wherein I just basically thought that when this is my mask, then this is the highest, then this is the highest element. But no, this is the basically the smallest element, because we go from here to here. This is the LSB, and this is the MSB, right? So this is a little thing to consider. Otherwise, I hope that I have made everything clear, right? So let us look at the code once, right? So the code goes like that. I had already told you about this particular thing. Okay, so I already told you about this particular thing, and I just was at my this particular, like I was at the mask which is represented by this, and I then got to a bit mask which is represented by, say, this. Then I got to bit mask that is somewhat represented by, okay, 1 0 1, and so on. Okay, having a little lag until 0 0 0 0 0 0, right? So this particular is the part where it gets interesting. Okay, and like this I would do. And initially I have this, and I have linked to this. So what I would do, that while my I, which I is like this, while my I is greater than 0, because when it would come to this, then my answer have come and my I has become 0, right? So what is my parent mask? What is the parent of this? What is the parent of this? This, right? So my parent mask is basically parent of this particular I, comma j first. This is the parent mask. And what is the parent remainder? Parent remainder is parent of I comma j dot second. Right? So I just created this, that for each particular mask, new mask that I have, I just add that if yes, if okay, that I have made true, that if from this particular mask I can go to this particular new mask with this particular new remainder, then I would have come from mask comma remainder. Right? So this is what I have. Like this, I made the parent. Right? So this is the parent mask, this is the parent remainder, this is the bit position, right? This basically means that my, like this, like say like this. This means that uh, I have one trailing zero. This means that ith element of my vector nums is getting placed at the front of the mask, right? This is what it is. This is of the new mask, right? Of the, that the parent mask is a better way to write, because that is the number that is getting. So simply, this is the kind of the index number of trailing zeros. I have, because this was sorted, so I just got that particular number first, and I just updated my I to be my parent mask and J to be my parent remainder. Like this, I calculated my answer, and this is basically simple reconstruction, and finally returned my answer. Right. So this was the whole possible idea that of this particular solution, which required DP bit masking plus reconstruction. So this is basically, let me go through the code once again. This is simple taking size, sorted it because I need the lexicograph graphical smallest permutation. If k is equal to 1, this is trivial. Permutation would be divisible. Does Leetcode parallel permutation this is lag? Please consider this much divisible and lexicographical smallest is the sorted one. Right? Interesting. So I just made a DP mask of mask and remainder tells us whether it is possible for me to make the remainder equal to rep using the subset represented by mask. For this, each len of mask denotes the number of digits that are there in my set constituting constituting of set bits of my bitmask, right? Simple function to make that. There is some sort of lag. Okay, so no why so much lag, right? So now comes the parent. This is for maintaining a parent from a particular mask, rim to new mask, new rim, right? Maintaining a parent, no, a link, like using this the backtrack to reform to there is a spelling mistake in a particular backtrack to reform required permutation. Interesting. Then I have my dp of 0 comma 0 because this means that taking no elements would imply that modulo k gives 0, thus dp of 0 comma 0 is true, right? So I have simply done it like this, that I have calculated all the power, calculated all the powers of 10. The reason is already been told previously because there was some issue of limit of long, right? So that's why I calculated it. The range is also conveniently I've taken 199, but it would a smaller would also work, right? So this is something that I've already told, that this is the new remainder, that that from this mask, if I take the ith unset bit and set it to make new mask, then new remainder which it would unlock is given by this. एंड प्रूफ हम इसका कर चुके हैं कि ये आया कहाँ से, ऑलरेडी मैं आपको बता चुका हूँ कि आया कहाँ से। और ये बड़ा ऑब्वियस है, And this is very obvious कि this is not possible. Basically, it's not possible to make any sort of permutation such that give me the remainder as 0. So I would simply return my empty vector, right? And this is basically jumping, I would say, to parent. This is basically jumping to the link, right? And this is the, like, if this is my bitmask, and from here I came to this, then I must have a link from this to this, right? So that's why I maintained link using that parent for this particular new mask, and the new remainder is the current mask and remainder. That from this mask and remainder I went to that mask, new mask and new remainder, right? So I simply had my answer and my parent mask to where I go, and parent remainder to where I go. That this particular bit position, only that bit is set. That bit is set, included. Okay, 1 second. Let it. Okay. Here only that which is set, which is included at the front of the which is included at the front of the new mask or parent mask, because we want the lex smallest permutation. Thus, it is best to sort it and then go to the smallest check of permutation at the last. Like he like I already explained it pretty well. There's no point of repeating it. That I want that I accept that there are two possible ways, like 12, 3, and 45, and 3, 12, and 45. But it is important that I put 3 first. Like 3 first instead of 12, because 3 would make it lexicographically smallest, right? So yeah, I've already explained that, and because I have sorted it, so when I would be iterating, then because then basically 3 would come later, then thus it would be checked at a later point. Thus it would update it over here. Over here, it would update it. Basically, it would update it again, right? So my link would be the one to the like smallest one, right? So like this, I jumped on and I updated my answer, and I pushed and I finally returned it, right? So basically, what I initially in the start of the video said that there were two lead code hearts that were kind of an extension of this particular question, were basically this very familiar question. Basically, this concept of parent jumping in dynamic programming is not very common. So I would urge you to see this one. That try these two questions also. That 1 second. Uh, yeah, over here it is. Okay, let's start the session. That longest increasing subsequence to, no, I think it was this. Right. Actually, this was a simple n log n segmentary based solution where even this was not necessary. I just did it because I thought that what if constraints were even harder, but this is not necessary. Right. What I wanted you to know is that here I have used the concept of DP reconstruction. Basically, a solution for this is n log n binary search or segment. But I deliberately did a M-square solution because I wanted to generate that longest increasing subsequence. Because here for each particular I, dp of I maintain the length of the longest subsequence that is increasing, right? Starting from that particular I, right? So for each I maintained its successor, right? So, and successor is basically the child, right? So I just first calculated that what is my maximum, right? Then I basically went on to my basically calculated which index it is, right? So I had my longest increasing subsequence, right? And till my index is not equal to child of index, basically till the last of my increasing subsequence. I just kept on pushing the nums of idx into my list, right, and updating my idx to the child of idx, right, and finally put the last element, right. The list, the LIS that I obtained is basically the longest increasing subsequence. I actually now not only got the length, but I also got which is that particular subsequence. Right. So this is an in-square solution. I would urge you to at least look into this. This is a very known, but just think in the direction of jumping to like kind of jumping to the child, and like this particular is the main thing that I wanted to tell you. Right. And this way, I think that you would be knowing that this is a pretty common way of finding the LIS using segment trees. Right. So this is, I don't think that this is tough. We did a pretty tough question, which required very much a lot of different things to be considered. Right. So let us run it once. It is getting run on my sample test cases, and yeah, this is getting accepted. So yeah, bingo, uh, bingo. We have solved this question, and all the best. Very sorry that if anything was bad, but and I really thank that I was also was not able to do it in my first school, and I took help and then understood it, and I hope that I am able to make you guys also understand. So yeah, this was it, and it was a great question indeed. Try it on your own, make DP tables, make understand why this is working, understand every line why this is working, why this and an empty vector. How is this jumping to parent working? And the most, I guess, the most toughest thing which I think many people who might have got accepted on this is that why sorting is working. That why sorting is actually important, because when I like kind of have a sorted order, right, and I have basically the ith bit representing the ith number from my vector. So basically, I am iterating from 0 to the last number, right? And during that, I am encountering the possible mask to new mask configuration in such a way that in my mask, a bit is unset. Say, like if I have only one bit unset type of masks, right? In that particular scenario, the one bit unset type of mask, which is like 111110, right, wherein like there could be many masks, right, like 0111 or 011 or 1101 or 1110. 110 is the thing that is coming at last, and that would be the last to impact it, because I need the smallest, the last, because it is 1110. This means that the bit is unset, right? This means that it is best to have the least significant bit unset, because that would be like the zeroth index element is the best element to come at front, right? It is the best particular element to influence my new mask, right? So think more. You think on yourself also that why this is important. Think about cases. You would be able to do this, and yeah, this is what that I wanted you to discuss with you all. Sorry if anything I'm not able to convey, but I just tried my best. And these are the other two questions that I would urge you guys to see. And yeah, all the best, guys. Let's meet in the next video.